Okay, I think we'll go ahead and get started. Welcome, everybody. My name's Curtis Smith. I'm a division director at the Idaho National Laboratory, also the general chair of the PSAM 16 conference, which is going to be held this summer. As part of the PSAM conference this year, we're trying something new with a series of, we're calling them pre-conference events. The first one was an interview with one of the founders of the IA PSAM organization, Professor George Pastelakis. That interview is actually online. If you go to the technical program area under the PSAM conference, you'll be able to see that. But today we have the second one. Today and tomorrow we'll talk about Bayesian inference and specifically how Bayesian inference is used in PRA, mainly for parameter estimation. And we'll go through many different topics. This presentation is being recorded, and so your participation consents to that recording. We do have the ability to field questions. So if you have any questions, please use the chat feature. Hopefully that is working for everybody. I'm also trying to check my email on the side. So I got 3 things going on at once, but again, if you have questions, try to chime in. And I have my email there. If you have questions after the fact, please feel free to reach out to me. Okay, with that, let's go ahead and get started. So we will have a 2-hour session today, and then another 2-hour session tomorrow. Same time tomorrow. We'll have a break roughly halfway today, and then same thing tomorrow. So let's jump into the slides. And as mentioned, we're going to go over Bayesian inference. And what we want to do is look at how Bayesian inference is used in PRA and what it actually means to say we're going to use a Bayesian method and the implications of that framework. And so we'll be able to look at updating our information. And we'll talk about things such as Bayesian priors. I will go over a couple of tools. We'll do some calculations in Excel, for example, calculations in OpenBugs. We're not going to go into details of the tools, but just realize that there are a variety of Bayesian-focused tools out available for your use. I happen to use OpenBugs a lot. It's an open source tool, so we'll see that. Now, one of the motivating factors for the course is actually we teach this class to organizations such as the U.S. Nuclear Regulatory Commission or NASA, for example. And we have a book that is kind of the technical basis for the course. That's a Springer published book, Bayesian Inference for PRA, by my colleague Dana Kelly and myself. We'll talk a little bit about what's in the book, and we'll actually hit some of the subjects in the book. We don't have time to go through everything that's in that text, unfortunately. But nonetheless, that book and then the slides, of course, will go through what it means to say we're a Bayesian or we're going to use Bayesian analysis for PRA types of problems. The types of problems that we'll walk through will kind of vary somewhat. We obviously will start with the easy problems, but then we'll get into some more challenging models and applications as we dig deeper and deeper. And so, for example, we'll start with kind of simple, what are called conjugate type of models, but then we'll go into topics such as how do you treat your data if it's uncertain. Could be a complicated subject, but you'll see the tools that we use nowadays allow us to have really complicated models and just simply crunch through the numbers without too much trouble. We'll talk about trending. We'll talk about extreme value models and other things. So a nice set of topics to kind of cover the landscape. So if I look at the textbook that I mentioned, picture of the cover right there, there are various chapters, and I've highlighted out of those chapters some of the sections that we will touch on and kind of go through in a sense in the slides. So the things that are not highlighted, we won't cover in the tutorial today or tomorrow. So for example, in chapter 3, we'll talk about what are called common aleatory models. Those are the probabilistic models that represent some kind of complex process. And we'll see what those look like for PRA applications. We'll talk about time trends, trending either using binomial or Poisson kinds of models. We'll go on then to chapter 8, talking about models for random durations or random times. And we'll see why that's important for PRA. We'll also look at how we might model failures with a repair process. And then, again, getting into more details, we'll move on to things such as how we treat our data if it's uncertain or certain. And then lastly, we will stop with a topic tomorrow on extreme value models. Okay. So first of all, a little bit of background on Bayesian inference for PRA and what it really means to say you're a Bayesian if you're using the Bayesian framework for PRA quantification. So this is going to be starting at a high level, of course, just trying to set the stage for the framework before we jump into the the quantification and the mathematical details. And there's a couple of key concepts that underlie the Bayesian framework. One of those is information, and so information is kind of what it is we're after to try to make sense of. What are we trying to characterize, if you will? And so information, of course, is a very generic word, and it can mean a lot of different things in different domains. And so we're going to specialize the word information, but just think broadly. You have a set of information in front of you. It could be things such as you have a component and you're testing that and you get failures and demands. That would be a set of information. Could be more rich things. So it could be maybe you have system engineering knowledge or component engineering knowledge, and you want to combine that with data, and so you want to mix and match kind of things. So the word information could be kind of really a rich word. But what we're going to do is really be able to translate information into a quantitative realm. And that once we do that, then we're really specifically talking about then uncertainty. So another way to think about this is we're taking information, kind of transforming that into a language that we call probability. And that's really uncertainty quantification in the Bayesian framework when we do that. So probability is our language as a Bayesian. And that's a very powerful concept. And as we'll see, we have powerful tools that help us on the quantification of that concept. So information is kind of a foundational bedrock. And it's important to realize, of course, even though we might have a lot of information, we don't have 100% knowledge of really anything. So not all of our information will be known. And even for the things that we think we know, we may be imprecise or we may be uncertain. And that's where, for example, the data uncertainty section would come in. Maybe you've recorded data, but maybe there's a fuzziness on that data. How do you account for that fuzziness? And so this idea of, again, assimilating what you know and making judgment in terms of a probabilistic realm, that's the process. So that's kind of depicted there in the right-hand side, where again, we start with information. What we do is we really describe that, in terms of models in the Bayesian framework, and we'll talk about either mechanistic or probabilistic models. But what comes out of that then is that uncertainty quantification that I talked about. We could use that to, design and operate systems, make decisions in general. And that process is really what we're describing today. And as a Bayesian, again, we'll look at quantifying basic events, for example, in a probabilistic risk assessment model. That will be one approach that we can take. So a very powerful framework here. We're going to be making predictions as we carry out the process described on the previous page. Because really what our models try to help us do is predict the world in some complex sense, but they try to help us make judgment, make predictions. And that's a tough thing, as we all know. I like the quote there from Mark Twain. It's not what you don't know that kills you, it's what you know for sure that ain't true. That's kind of another way to characterize uncertainties, I guess. But and the picture to the right there shows, sometimes we know a lot, sometimes we don't. But what we do is we do take the things we know, we will put those together in a Bayesian framework, and then we'll make predictions. Those predictions will be uncertain, just like the magnitude of the size of the iceberg below the water. We might have a general sense of what that might be, but there's uncertainties there. But nonetheless, that's the process, and it's a very powerful process that we use in PRA. Knowledge and information help reinforce our predictions, and it's a cyclic thing. As we make predictions, we tend to gather more information, and we can update those predictions. That process is called Bayesian updating, and we'll see how that works. Okay. But again, remember that what we know is incomplete, hence we have to go to probabilities and uncertainties, and we'll still be able to make predictions even though we don't know everything, but we'll do the best we can. So sort of recapturing that idea, then this translation between information and uncertainty. When we follow that process, we can use a Bayesian approach or a Bayes-Laplace approach. We'll talk a little bit more about Laplace and why he shows up on this slide. But this process that I'm describing today and tomorrow is just called the Bayesian approach or the Bayesian method. It gives us a way to talk about probabilities for specific outcomes of interest. If we're looking at a PRA, those outcomes might be a component fails to start or a component fails to run. And so what we're going to be able to do is describe probabilities related to those outcomes. And so the real world part of that statement, of course, is the outcomes. Either the component starts or it doesn't. And we don't know if it's going to start the next time we go try to start that component. But nonetheless, we'll be able to describe a probability that's centered around that outcome. And then we factor that probability into our risk models, our reliability models, and then we bring that together in a complicated model where we put many components together, many initiating events if we're doing a PRA, and then use that to help us guide the risk and safety for facilities. And that's really the decisions that we're talking about, is the outcomes of our risk and reliability models. What are we going to use those for? Okay. Now, the information that I'm talking about, that's at bedrock. Again, that could be a really rich set of things. It could be, expert elicitation, the information that comes from experts. It could be operational data. It could be laboratory test data. It could be both. It could be data that's kind of collected in real time that's coming up. We might have simple models, might have complex models. Hopefully we don't run into the last bullet though, or we just make something up, but information can be complex. And looking at these bullets here, some of the information, so for example, like operational data, might be a very strong influencing factor on your uncertainties and your probabilities. misinformed or not very well informed expert elicitation might be very weak evidence. And you could factor in the strength of your evidence into these processes. And we'll see examples of that later. So let's first go through an example. I'm a nuclear engineer, so I'm going to kind of borrow an example that you would typically see in a nuclear power plant probabilistic risk assessment. And that example will be, we're going to represent my facility and the possibility that I could lose offsite power, or LOSP. Now in my hypothetical facility here, I have some emergency diesel generators, or EDGs, and those sit there waiting until I lose offsite power. And hopefully these emergency diesel generators will start once I lose offsite power. But if they don't start, that starts to get into more complicated scenarios. So in our model here, what's called an initiating event is the loss of offsite power. And that triggers then the diesel generators to start and run. So you can see this model is going to start to have multiple pieces. It will have, what's the chance that I lose offsite power? What's the chance that the diesel does not start? What's the chance that the diesel does not run? And so I need to define kind of what is the failure space in this scenario? What's the success space? And again, this is a hypothetical facility, but let's just assume that success is if I start one of the two diesel generators and it runs for 6 hours to cool the plant down, run the plant for 6 hours, whatever it needs to do, remove decay heat and so on. But if one of the diesels runs for 6 hours after I lose offsite power, I'm okay. What that means is if one diesel fails, I'm still okay. But if two diesel fails, then I'm not okay. So I've defined now my success and failure spaces. I could then take that information and put together a PRA model. And what that might look like then is shown on slide 9 here, where I'll have an event tree, which is this little structure here on the left. The event tree then starts with the initiating event where I lose offsite power. And I have a parameter that I call lambda LOSP. That's the frequency of losing offsite power. And then I question my diesel generator. Either that system works, which is the up branch, and I'm happy, which is the down branch, and I'm not happy. And the system failure probability is given by this parameter called P subscript DG, or the probability that the diesel generator system fails. Now, to describe that system, typically what we do in PRA then is create a fault tree. And so for that system, for failure, remember we just said both diesels have to fail. And so that implies I have this AND gate where diesel A has to fail and diesel B has to fail. And then we look at, okay, well, what does it take for diesel A has to fail? Well, I have two failure modes that I'm going to worry about. I could have more, but in this simple example, I have two. I have the diesel fails to start, the FTS, the diesel fails to run, FTR. If either one of those things occur, I don't get through that 6-hour mission time. I don't provide the plant with electrical power to run pumps and do other things. So that's a failure. And either one of these can fail the diesel. And so I'm able to start putting this fault tree together with the event tree to get combinations of failures. So it'd be things like loss of offsite power, and diesel A fails to start, and diesel B fails to start. Or a combination would be loss of offsite power, diesel A fails to start, diesel B fails to run, and so on. So a simple model. Now, what's important for us for this topic is that each of these parameters, whether it be the initiating event, the loss of outside power, or these lower level basic events where I have probabilities, I need to describe them probabilistically. I need to tell you what is my state of knowledge about the parameters. I need to describe my uncertainties for diesel A fails to start, diesel A fails to run, the frequency of losing offsite power. Because it's not a set value, but it's a distribution of what is possible given my model and my state of information related to the process. So in other words, I need to come up with these little green distributions for each of my parameters in my PRA. And we're really going to be spending then the next several hours today and tomorrow describing how do we come up with those green distributions? How do I take the information? How do I take the models? How do I put that together so I can come back to this PRA model and fill in the blank, so to speak, for the parameters that you see here? Yeah. So big picture, that's what we're doing. So let's look at the process from a sort of real world perspective to get a better understanding. And that's important because what we want to do is be able to model processes. And if you don't understand the process in terms of physically what's happening, it becomes challenging to represent a process probabilistically without that knowledge. Excuse me. And so we kind of have this complex diagram here where from left to right we're going through time, but the kind of back wall here is the physical process that we would see in the real world and that we're trying to mimic in our PRA. So in other words, we start operating my nuclear power plant, and we keep doing that. We keep operating until I get a loss of offsite power, and that's really this first breaking point. And we don't know when that's going to occur. We don't know when I'm going to lose offsite power. So there's some process here that could describe that. And that initiating event occurs, stochastically. But once that initiating event occurs, then of course that's what triggers my plant safety systems. That'll trigger the diesel generator to start. And either the diesel starts or not. I then if it starts successfully, it might run, but then fail. And so that might be another process I have to model. What's going to happen after it starts, but fails at some time. Now, if it fails, I might be able to fix that. I might have operators that can restore that. In my simple example on the previous page, we did not allow for fixing the diesels, but I could put that in. And then I might also be restoring my offsite power. So I might actually, fix the offsite power without even worrying about the diesels. If that happens quick enough, then I'm okay. In my simple example, I did not allow for this, what's called restoration of offsite power. But in a real PRA, we would typically include that. So in a complex model, or a real PRA, you would typically see all of these processes represented. You would definitely see the initiating event, the loss of offsite power. You would see the fails to start, the fails to run, maybe or maybe not the recovery of the diesels, maybe or maybe not the recovery of offsite power. But these are all different processes. So the back wall again is kind of the reality of what's going on. And now us as analysts, we need to represent the process, and we have different models to do that. And that's kind of then on the floor part of this diagram. So for example, to represent initiating events, something that's stochastic like losing offsite power, we tend to represent those using what's called a Poisson model. And we'll see this in a second. But the Poisson model gives us a very convenient probabilistic model to represent random occurrences of events like losing offsite power. Now, is that model right? I don't know. We can check the validity of models, but the Poisson is just one model that we have. It's a very common model, and it's typically the one we use for initiating events. But again, it's just a model that's trying to represent the reality. The diesel fails to start. The model that's like flipping a coin. You push the button, does it start or not? It's a yes, no kind of a question. The model that we tend to use for those kinds of processes is a binomial. The diesel fails to run. Similar to the stochastic initiating event, it's some occurrence over time, and like the initiating event, we can use a Poisson model. The operator recovering the diesel, that might be, again, a model over time, and again, a Poisson model may be the preferred model there. And then offsite power restoration. Poisson might be a good model. But again, some of these other more complicated processes like offsite power recovery, you may get more complicated models. You might use an exponential model or a log normal model simply because if you collect data, it looks like it's more of a log normally driven process, for example. So again, take all of these model declarations with a little bit of grain of salt, because these are all just my assignments. I'm saying Poisson represents this, Poisson represents this, binomial represents that. I need to justify that. And again, there are ways to do that. So if I pull the PRA model together, what comes out are called minimal cut sets. You see those here. Those are simply just the combinations of ways to get to the bad outcome that I mentioned. So we have loss of offsite power. The little asterisk means and. The loss of offsite power and diesel generator A fails to start and diesel B fails to start. So that's one way to get to this unhappy face in my model. Another way is offsite power loss, fails to start, fails to run, or A fails to run, B fails to start, and then lastly, A fails to run, B fails to run. And again, there's assumptions behind these combinations. The assumption of 6 hours. If we run for 6 hours, we're okay. We will avert core damage. I might need to do a thermal hydraulics calculation to get that 6-hour time. That's, we're not talking about that in this symposium. I did not put the recovery possibility in these cut sets, so I could make it more complicated. But again, this is a very simple model to talk about the parameters, because what I want to do is be able to talk about how do I get the distributions for each of these elements or variables or basic events in the equation here. Okay. Again, if we wanted to put recovery of a diesel generator, what we would do is we would take those cut sets and change them to look something like this, where we would have more details. And so the first new variable here would be offsite power non-recovery. In other words, the probability that we do not recover offsite power in 6 hours. And then we would need to have a model for that. And then the second part would be the diesel, if it fails, that we don't recover the diesel, or EDG non-rec. So both of these represent a probability that we don't do something. We either don't recover offset power or we don't fix the diesel generator. Okay. So let's talk about how we are going to quantify the probabilities. We're going to use Bayes' theorem. And I've dissected Bayes' theorem here. You may or may not be familiar with this, but if you're familiar with this, Bayes' theorem is an equation that has a relationship between kind of our state of knowledge, our model, what we believe about a process, and how we're going to put that together in order to get a sort of an updated set of knowledge. And that updated set of knowledge is on the left-hand side here, and we call that the posterior. But how this works is we put a few things together that are critical on the right-hand side that gives us a probability distribution. And we're going to start with a probability distribution called the prior. That prior, again, is specific to what it is we're modeling. So in other words, if I go back to my equation here, I need to have a distribution on loss of offsite power that I'm going to update. I need to have a prior for that. I need to have a prior for diesel generator A fails to start, B fails to start, and so on. So I'm going to put these pieces together in order to come up with a posterior distribution. And that posterior distribution then is what we put into the PRA model. So that our goal then is to use Bayes' theorem here, quantify the numerics, and end up with a probability distribution called a posterior that I can then put into my PRA model. So in other words, running this equation gives me these green distributions. That's our goal. So in addition to the prior then, we have these other two parts. We have what's called a likelihood. Also, it's the probabilistic model, also called the aleatory model. So there'll be a couple of names that this box goes by, but likelihood is typically what you would see in a textbook. And then there's a normalization constant that we'll talk a little bit more about. But really, these three pieces here are the key. We have some set of knowledge that we wrap up into a prior distribution. We have a probabilistic model and some data that go along with that process that we put together. We normalize it, and doing that gives us a posterior. In other words, we take what we know, combine that with a probabilistic model and any evidence, any data related to the process that we're representing, and we end up with a new distribution. So the process, what goes in the likelihood, ties back to this figure. So for example, if we're looking at the frequency of offsite power, the process that we're going to use, at least for today, is a Poisson model. And so I would need to have a probabilistic model for the Poisson. We'll see what that looks like, but that would go into the likelihood box. So in other words, this box, when I'm going to characterize loss of offsite power frequency, this box is going to be where the Poisson model lives. And also any data related to losing offsite power would also go into this box. What that data looks like. If we've looked for loss of offsite power events, we would count those over some period of time. So maybe we've seen, 2 loss of offsite power events over the last 20 years. That kind of data plus the Poisson would go into this box. Okay. So again, we're taking Bayes' theorem to come up with those green distributions. Why are we doing that? Well, some really smart people several hundred years ago figured out there's a way to take this idea of probability, there's a way to take probabilistic models and evidence, mix those together in a mathematically coherent way to make predictions. And it turned out those predictions seem to be, a good way to look at complex problems. So Reverend Bayes sort of described the process, I will say, but then Laplace was really the first one who kind of took this idea of Bayes' theorem and operationalized it. In other words, Laplace really figured out the math to how to do this for real problems. Now, they weren't doing PRA in 1774, but they were doing a lot of science. And science is very similar in the sense of we have a process, we have operational data related to that process, we have models related to a process. How do we take what we know, combine that with the models and the data? Now, in the case of Laplace, he was using Bayes' theorem. Well, it wasn't called Bayes' theorem, but using this mathematical way to combine information to look at predictions related to masses of planetary bodies like moons and planets and whatnot. And so he, of course, used this equation to look at, estimating the mass of Jupiter, the mass of Saturn. If you look at the details, it's very interesting, but he would look at, okay, what do we know about the mass? So things like using a uniform prior, mainly to help out the mathematics, was part of the equation. So you'd we think the mass of Saturn is between this and this point. We don't know anything more about that. It's just between those two sort of upper and lower bounds. The data and the probabilistic model that would go here, we're looking at planetary motions of satellites rotate or going around Jupiter, satellites going around Saturn, and the data that was collected by observing those with telescopes. Put all that together, and he was able then to make a probabilistic prediction. He predicted, okay, here's the mass of Saturn. And then not only that, but since he had a distribution, he was able to say, I know that uncertainty to some confidence. And so he was able to quantify, the error and the odds. And when you use the term odds, that's just another way to say your probability level. So in other words, in his publication, he claimed that he was in error by less than 1%, by no more than 1%, and he was very certain of that. And so he gave odds of 11,000 to 1. Now, what that really means that he thought his potential error was 1%, but he was 99.991% confident of that statement. And again, the only way you could say that is by using this framework here, by using the Bayesian approach to quantify the uncertainties through his state of knowledge, plus the probabilistic model, plus the data that was collected at that time. The mass of Saturn, the sort of best estimate for that has changed over time, of course, because our scientific instruments, have changed. But the estimate has only changed by about 0.6%. So his 1% claim, I think he nailed it. In other words, he probably could have said, I'm really, really highly confident, it won't change more than 1%, and that he would still be right. But anyway, 99.991 is a pretty high degree of confidence. Okay. Who's joining? So if we look at then sort of from a process versus a formulaic view of Bayesian inference, what we're doing is, again, we're taking information related to the parameters in our PRA. The knowledge that we have behind that could be historical information, could be engineering knowledge, could be observed data. We may have a lot of data, we may not. It doesn't really matter. All as a Bayesian is, we're trying to quantify the uncertainty in what we know. And so we're not sort of prejudged in terms of how strong that evidence is, because once we go through the process, we'll be able to make a claim of how strong our knowledge is, very similar to what Laplace did on the previous page. Okay, so Bayesian approach is really, again, just a formal mathematical way to combine information. So from a flowchart kind of process on the left here, we take the prior, we take our probabilistic model and data, we combine that through Bayes' theorem, we get a posterior. Expanding the simple equation that I dissected a couple of slides ago, what that looks like is our distribution is the pi, and so we start out with a distribution pi 0, that's the prior. We're going to update that and end up with a pi 1. We do a Bayesian updating process to end up with the posterior. And in the case of, let's say, the initiating event loss of offset power, lambda, how you would read this is We're going to get a distribution on lambda given, the vertical bar means given some data and really a model. I mean, I should expand this. It's data plus a model always. But that will tell me what is my new state of knowledge. To do that, I need to have the parts that we talked about previously. I need to have a likelihood function, aka probabilistic model, and a prior. And then I need to normalize that. And that's where the complicated part of Bayes' theorem comes in. This integral, because the normalization simply says, kind of look over all possibilities of the data, the model, the prior, combine those together over, plus or minus infinity. And if I could do that, that will normalize the top part here, and I'll get a proper probability distribution. And we all know that this this integration can be a difficult thing to do depending on what the equations or what the models, what are the formulas that we're going to have to integrate. So some of the times math's not so bad. A lot of the times the math is horrible, but fortunately we have numeric tools nowadays to help us out, as opposed to Laplace, who had to figure out the math and do all the math by hand analytically at the time. But we're beyond that now, so we have a much easier time. So let's go into another example here. I'm gonna look at a parameter, temperature sensor fails. So let's assume I have a PRA, someplace in that PRA, I have a temperature sensor, and if it fails, that's bad for some reason. What I'm going to do is just follow the process that I showed on the previous page. How do we actually bring all this information together? What does it look like in terms of the actual numbers and outcomes? So first of all, let's focus on the prior part. So I've kind of shaded that area here. I'm looking at temperature sensor fails. I might know something about that, I might not, but fortunately, a lot of components and their probabilistic performance have been tabulated in databases or handbooks. And so I might have a database that says, okay, for generic temperature sensors, they fail with this rate. And so this would be a common thing. You'd go to the handbook, you would see temperature sensors. It would probably say something like the sensor fails with a average of 1 × 10⁻⁷ per hour and an error factor of 10. Well, this mean and error factor relates to a log normal. So in other words, somebody has done analysis or expert elicitation that says the failure rate is a log normal distribution with these two parameters, 10⁻⁷, error factor of 10. It's like a mean and standard deviation on a normal distribution, kind of similar concept here. I've plotted that, that's the red curve here. So on average, the failure rate is 10⁻⁷ per hour. That's a pretty reliable component. 10⁻⁷ per hour is pretty reliable. Okay. That's only one part of the Bayes' theorem, though. I need to have then a model and the data that go into that model related to temperature sensors. So I put the prior aside for a second. I now pick up what is going to be the model for this. So the probabilistic model that I'm going to use in this example is it's going to be some kind of failure occurrence over time. It's going to be very similar to the diesel generator fails to run, a failure over time. And we said that was going to be a Poisson model in my earlier example. And the Poisson model is shown here on this page. So the probabilistic model, my function of X number of failures given a failure rate lambda is the Poisson. Again, that's an assumption. I'm not sure if this temperature sensor actually behaves like a Poisson process. I can check that though. but again, that's a we kind of have go-to models in PRA and reliability applications. A Poisson is a very common one to represent occurrences over time. What that model looks like is simply this, the Poisson equation. So we have the failure rate, the time involved, the mission, X number of failures, either the minus failure rate times time, X number of failure factorial. So I have a model, but I still need data related to that model. And what Poisson data would look like, and again, this is just a hypothetical example, but let's say I have run temperature sensors, and I've run them, so I have a whole bunch of these, and I've run them for a collective total of 1,554,000 hours. So I must have a lot of temperature sensors. So I've run these for a long time, one of the two or both. And out of all of that time, I've only seen one failure. So I would say X equals 1 in terms of this equation. T equals 1,554,000. Lambda in this equation is the same lambda here. The lambda really is represented by this distribution. And then when we put this together, when we put the Poisson model together with the data, that's again called the likelihood function. That's plotted here. The green curve. I then have my three things I need to do Bayesian inference. I need to have a prior, I need to have a model, and I need to have data. And once you have those three things together, you can do Bayesian inference. So I have my prior, I have my model, I have my data. I then run all of that through Bayes' theorem, and I get a posterior distribution. Now, in this case, I actually ran this example using the OpenBugs tool. We'll talk more about that later. But what comes out of the process, what comes out of OpenBugs itself is another distribution. And remember that distribution is called the posterior. It's this sort of brown tan shaded curve. So we started with the darker curve, that's the prior, and we said based on this model, the Poisson, and based on the data that I've seen, I'm going to start with this, but I'm going to modify it to this new curve. And I would use that new curve then in my PRA. So wherever the temperature sensor failure event occurs in my PRA model, I would place this brown curve into that PRA model. And so we're not going to talk about how to do PRA at that point. That's a subject for another class. And in fact, I think the next PSAM seminar that's coming up early in May is going to talk about a tool called Sapphire that Jim Knudsen will go through. That's a 5-day course for a couple hours each day. Sapphire is where we would take the fault trees and the event tree models that we talked about earlier, put them into the code, and we would then also put this distribution into Sapphire. And Sapphire knows how to take that distribution, knows how to take that uncertainty and propagate it through both the fault tree and event tree. But that's, again, that's a different class. So any questions? Again, if you have questions, the chat function is open, I believe, hopefully. But the process, if we recap the process, I have to have a probabilistic model for the process of interest. And we looked at some processes for fails to run, fails to start, fails to recover, initiating events, and so on. I have to have what's called an aleatory model for that process. So it's important to understand the physical, the real world. What is the process that's driving the outcome of interest? You also have to have the second thing, a prior distributions for the parameters in that aleatory model. I need to describe what do I know about the parameters in that model representing the process. And then the third thing I need is data related to the process. So you might ask, well, what happens if I don't have any data? Well, if you have no data at all, the prior and the posterior are the same thing, which is a nice feature of Bayes. If you could put down a distribution, a starting point, at least you have a starting point. You have something that says, here is my state of knowledge. Now, as you collect data, then that state of knowledge will change. But we need those first three things. We need an aleatory model. We need a prior distribution on the parameters. We need data related to the aleatory model. We can then run Bayes' theorem once we have those three things. That's step 4. And then step 5 is check the validity of the model. And this is a general process. This is, again, what we use for parameter estimation in PRA models and reliability models for that case, too. It's not just risk models, but any place where we're going to talk about probability of something, here's the process to talk about how to come up with that probability. Okay. So let me take a short break here. We'll take a 10-minute break and come back and talk about open bugs and conjugate calculations. That's the simplest one. Let's see, I think I have a question in the chat. Could you elaborate again what the probability distribution graph you presented means? Is the scenario... So let me go back then. So the probability distribution here represents what do we know about the rate of failures of a temperature sensor. And so that's our starting point. We then update that with our model and data to end up with this brown curve. So I've overlaid the two, our starting and ending. But both of these curves represent the same thing. Both of them represent a temperature sensor failing, and specifically the failure rate. How likely is it for my temperature sensor to fail over time? And it's essentially the same thing we're looking for here. So in our loss of offsite power model, the green curve that I talked about, I'm going to get a distribution on the frequency of offsite power loss. The diesel generator A fails to start, the diesel generator A fails to run. I'm going to get the green curves using the process described here. So my green curves for my loss of offsite power is sort of the equivalent of the brown curve here for my temperature sensor. And it's just a failure rate in this case, and it says we don't know the failure rate exactly. There's some uncertainty about that.